Hi everyone. I welcome you all for another brilliant presentation on another beautiful subject that is electronic devices and circuits. This is one of the very important and topmost scoring subject in GATE examination as well as in UPSC's IAS engineering service examinations also. Not only that, in many other technical competitive examinations too. So today I am going to start about this subject, and we will see the basic important things of this electronic devices and circuits, right? As far as your gate examination is concerned, you have two separate line entries under section 3, that is electronic devices, under which it is given that the basic introduction about the classifications of materials based on their energy band diagrams and how the materials are classified and what are the different types of materials and how they can be classified or differentiated based on their energy band structure. And afterwards we will see their differences and then their properties and so on. And after that, slowly we will see the remaining topics also, right? So we will move into the subject. Let us enjoy today's presentation, right? Yes, I welcome you all for another beautiful presentation on another important core subject of electronics is electronic devices and circuits, which is a very important subject and most scoring subject, especially in gate examination point of view and even in UPSC's IAS examination as well as many other technical competitive examinations, right? This is the very basic foundation subject in fact, right? So as far as your gate syllabus is concerned, this is given under section 3 of the overall syllabus prescribed by Indian Institute of Technology Kanpur, which is going to be conduct the gate examinations for 2023, right? Okay, if you see your section number 3, there are two separate line entries have been given, and the first line entry is briefly they have described about energy bands in intrinsic as well as extrinsic semiconductor, and then equilibrium carrier concentrations, and then direct and indirect band gap semiconductors. That is what under your first part of it. And coming to the next line entry of under section 3, nothing but under this EDC subject, you will have the carrier transport. It describes about the diffusion current, drift current, mobility, resistivity, conductivity, and then generation, recombination of carriers, right? And then you will have the Poissons and continuity equations. These are what the basic syllabus, actually the brief syllabus given under section 3 of your gate syllabus for electronics and communication engineering graduates, right? This is given under section 3 of your EDC, right? Today I would like to explain you the basic introduction or the basic foundation of this electronic devices circuits, right? So today I am going to give you the basic information, okay, basic background otherwise, or otherwise you can call as some introduction also, right? Introduction. In general, in general, the electronic devices is starts from the origin of classifications of materials normally, right? So this subject describes or discusses about the classifications of material, how the materials will be classified, what kinds of materials will be there, means what types of materials are there, and what are their properties, and how they will behave, and how they will, I mean, works, that we will see in today's presentation. Right? In introduction, we will see what are the classifications of the materials. Classifications of the materials. Right? Classifications of the materials. So, the classifications of materials basically, again, it is classified, or the materials can be classified based on one important parameter, that is called the energy band diagram. That is called energy band diagram, or otherwise it is also called as energy gap, also called as energy gap, right? Energy gap diagram. So this is very important topic actually, energy band diagram or the energy gap diagram. Based on this particular energy band diagram or energy gap diagram, the materials will be classified, right? The materials are classified into basically three important categories. They are categorized into three important categories. Those are called as insulators. The first category is insulators. This is the first category. The second category is conductors. The second category is conductors, and the third category is semiconductors. Right? The third category is semiconductors. These are the basic three important categories or classifications of the materials which are categorized or classified based on the energy band diagram. Right? What is the energy band diagram? What is the energy band diagram? It is a diagram which consists of basically two bands. There are two bands. They are separated by an amount of energy. That is called energy band diagram. I will explain you about the energy band diagram. Right? We'll see what is energy band diagram. Energy band diagram. Right? What is this energy band diagram? It is nothing but actually there are two bands will be there. There are two bands basically like this. There are two bands basically. These two bands are separated. If you see, this is the gap between these two bands. This is the gap actually between these. This is band 1, let us say. This is band 1 or band 2. Band 2, or otherwise you can call this as band 1, whatever you, don't worry, you can write anything. This is the band 1, and then this you can call band 2, no problem. This is band 1 and then band 2. Two bands are separated by a small amount or some amount, not small amount, some amount of gap. This is called, this gap, whatever this gap you are able to see here is called as energy gap. This gap is called as energy gap, right? It is called energy gap, and it is represented by E suffix G. E suffix G, right? What are these bands? And furtherly, these bands can be called as, the band 1 is called as valence band. This is called valence band. What is? It is called valence band, or in simple you can write VB. This is band, the bottom band is called as valence band, whereas the uppermost or the upper band is called as conduction band. This is called as conduction band, or you can call as CB. right? There are two bands in general. One is the valence band, second one is the conduction band, and these two bands are differentiated or separated by an amount of energy, Eg, that is called the energy gap, right? For some types of materials, the energy gap values varies actually depending on the type of the material. This energy gap will be maybe less, maybe zero, maybe very high. Clear? So the energy gap will be zero or less, or it is more. Depending on this energy gap value, the materials are categorized into three categories, right? Say for example, if the energy gap is more, let us say the energy gap, and one more very important parameter or point that I need to, okay, to inform you is that the energy gap Eg is proportional to, is depends on temperature. It depends on temperature T. Remember that energy gap is depends on temperature T. Very important. The energy gap value, this will depends on the temperature. How it will depends? How the energy gap will varies with the variation in the temperature, that I will explain you in the further subsequent presentations, right? At this point of time, you just note down that the energy gap depends on temperature, right? Now let us see, say for example, so these two bands are there, valence band as well as the conduction band. And in the first case, what I am going to explain you is that, let us say the energy gap is more. For example, the energy gap is more. Normally, if energy gap is more, is nothing but the gap is more actually. The gap is more between these two bands, the gap will be very more. Okay, what is the meaning of this valence band and conduction band? What these bands will do actually? What is the purpose of these bands in general? If you consider any material, basically that material is consist of a structure is called a lattice structure. In the every lattice, you will have unit cell. You will have a small unit cell. It is a combination of multiple unit cells will be there, that is called a unit cell, and finally overall we can call it as a material. And for more information, I suggest you that please refer the textbook Material Science by R. Mugam, an excellent textbook. There you will find an excellent information based on the types of materials. R. Mugam is the scientist, author of the textbook. It is a very beautiful. Or even the materials, the material science by, I think, the Streets Man. The Street Man is also another excellent book, right? So as far as our subject is concerned now, let us see that what is this valence band will do. Normally, if you consider any atom, for example, if you write the electronic configuration of that particular atom, you will have in the outermost orbit, you will have certain free electrons, or those free electrons are called as the valence electrons, right? At this point of time, you just note on this much only. In the further subsequent presentation, everything, whatever I am delivering you now, whatever I am discussing you, it will be connected as you move on further presentations, right? At this point of time, remember that. So what this valence band will do, it consists the free electrons. The valence band consists of free electrons. Free electrons is nothing but those are the electrons which will be there in the outermost orbit. Clear? So there will be free electrons in the valence band. Here electrons will be there. Some electrons will be there in valence band. Now, these electrons which are there in the valence band, these electrons, we should make these electrons to move to the conduction band. If the free electrons or valence electrons, if they are lying in the valence band itself, there is no use of these electrons. You should make the use of those electrons. For that, what we need to do is that we should make them to move these valence or free electrons from valence band to the conduction band. Then only the conduction process will take place. Thereby the electricity, the current, the flow of current will take place. Thereby your conduction will be. That's why it is called a conductor. That is the definition of a conductor, right? Once the electrons will move from valence band to conduction band, right? Thereby the conduction will take place, right? That is what the ultimate our motto or our task is. That clear? Now let us see. We are discussing about if the energy gap is more, then what will happen, right? Normally, if the energy gap is more, it is very difficult for electron to move from this valence band to the conduction band, right? In general, if the energy gap is more, means that this particular more energy gap will fall under the category of insulator. The material which will have the more energy gap will fall under the category of insulator. What is the insulator, by the way? What do you mean by an insulator? Insulator is a material which does not allow the current to pass through it. Thereby, there is no conduction at all. Clear? So, the material which will not allow the current to pass through it, that is what that material is called an insulator. Say for example, the board which I am writing, I am explaining you, it is example for insulator. And then the wood, the mica, and the paper, is it not? For example, the diamond is, these are the examples for insulator. Means there is no conduction, current will not pass through these type of materials or these materials. That's why all these are comes under the examples for this insulator. For these, say for example, if you take the diamond, if you consider the diamond, the energy gap is very more. It is approximately, it is greater than, or for a diamond, it is about 6 electron volt. The energy gap is approximately 6 electron volt actually. The energy gap value for diamond is 6 electron volt. Normally, the energy gap is measured in electron volts. Remember, the SI units for Eg is electron volt, and for diamond, it is 6 electron volt, which is a quite heavy value actually, a quite greater value. So, the energy gap of 6 electron volt is a very quite higher value actually. So it is very difficult for an electron to cross this much higher energy gap, and it is very difficult for electrons to move in the conduction band. Thereby the conduction will not take place here. That is why this material is called insulator. Therefore, for insulator, the energy gap value is about 6 electron volt and even more than this. The energy gap is more for insulator, right? That is what. Next, coming to the conductor. What do you mean by conductor? It is quite opposite to the insulators. It is quite opposite to, exactly opposite to the insulator. Insulator will not allow the current to pass through them, whereas the conductor allows the current to pass through them, right? As a definition, if you want to define that, a material which will allows the current to pass through it are called as conductors. The material which will allow the current to pass through it is called as conductors, right? Human body, let us say for example, our body is a good conductor. Our body allows the current to flow through our body, right? Like that. So metal is a conductor, is it not? Like that. These are the examples for conductor, is it not? Okay, if you consider the conductor now, say for example, and how the easy energy band diagram will be shown for this insulator, let us see, then I will explain you about the energy band diagram for the conductor, right? So for insulator, if you see, for insulator, the energy band diagram will be like this. This is, say, the conduction band. I mean, this is CB, conduction band, right? This is the valence band, okay? Valence band, you can show like this. Eg is approximately, it is 6 electron volt. This is what for energy band diagram for insulator. Whereas for conductor, it is very high actually, it is quite high. This is very quite high value actually, the energy gap is very quite high value. Therefore, difficult for electron to move from valence band to the conduction band. Whereas coming to the conductors, what is a conductor? Conductor is nothing but material which allows the current to flow through it. So if you take the energy band diagram, okay, EB diagram, otherwise energy band diagram of conductors. Clear? If you write the energy band diagram, it will be looks like this. This is, or sometimes both bands will be, the Eg is 0 here, let us say, and this is something like this, or otherwise even I can show you that as a, this is I will show you, I represent with a red marking. Let us say this is your conduction band, let us say this marking, this red one is your conduction band, this is your CB, whereas here, from here, this is what my VB, this is my VB, and then this is my CB. Are you able to see? No, this is my CB, conduction band, and this is my valence band. If you can able to see this particular portion, this one, I am marking it as like this. What is this? This is overlapping region. This is the region where both bands are overlap to each other, thereby there is no energy gap at all. The Eg value is 0 here. This is the overlapping. Here means it indicates that the Eg is equal to 0. Eg, the energy gap is 0. Therefore, if you see the conduction band and these are the valence band, therefore there is no energy gap, there is no gap between these two bands, right? Thereby you can say that the energy gap is 0. If the energy gap is 0, then what will happen to the electron? Normally you will have free electrons, no, in the valence band. You will have free electrons in valence band. If there is no gap, it is very easy for electron to move from valence band to the conduction band. Very easily they can move from here to there. Is it not? That's why, therefore, thereby electron can easily move from valence band to the conduction band without much difficulty. Therefore, the conduction is very good. The conduction is because that's how the material allows the current to pass through it. That's why these are called conductors, right? I think you understood. Therefore, the energy gap is 0 electron volt for conductor, right? This is what the conductor. Whereas how it will happen actually, I want to discuss some points here. Conductor, basically, say for example, how these electrons will move from valence band to, can directly these electrons will move from here to there without any additional force or additional application, without any other applications? Can electron easily moves from valence band to the conduction band? No, not at all. It needs some applied electric field. It needs some applied electric field. How it can be shown? For your better understanding, let us see this. Say, I will consider a metal. Let us say this is a metal bar. This is a metallic bar or metal bar. Okay. So in metal bar, it is a metal basically. It comes under example of your conductor. And normally, say for example, before heating, it is a like it is a raw material. Now but inside it actually the concept of your valence band and conduction band will be there definitely. Physically you cannot able to see, but internally this process will take place and it will be there actually. This is a metallic bar, say for example, and in which the valence band as well as conduction bands definitely will be there. Now what will happen is actually, without application of your electric field, I think it is of no use. Now, if we want to make the use of the free electrons which are there in the valence band, then I need to apply certain electric field. It is nothing but heating. Otherwise, you can call it as heating. We can apply some heating element, and we will heat this. Then it will be gets heated. Is it not? Once if it is heating, then internally the process will take place in this. Otherwise, okay. Or otherwise, if you take some conductor or some metallic, if you apply some electric field here in this way, this is the applied electric field E. Okay, it is applied electric field volts per meter. Let us say it is called as volts per meter. Because why volts per meter? This is applied electric field. Sometimes in some textbooks it will be represented by E, or in some textbooks it will be represented by capital V. But the SI units for it is volts per meter, because what is the length of the material that you are taking per meter, how much volt we need to apply. Therefore, that is why volts per meter is the unit of this applied electric field. Now, let us say for example, I am applying certain electric field. E is my applied electric field. Assume that there are some valence electrons are there here. Let us say for example, now I am applying slowly, I am increasing this. Let us say it is a variable one. Show the arrow mark. If I am increasing from 0 to 1 volt, 2 volt, 3 volt, 4 volt, like that, I am going to increase this little bit step by step. Right? So as you increase the voltage, applied electric field, otherwise, slowly your whatever the electrons are available here, slowly they will get energized and they will move from valence band to, they will try to move into the conduction band. Right? Because of this electric field, the electrons get energized and these electrons will acquire some energy. Thereby, they will have certain velocity and they will move with some velocity, and they will move from here to there. They will comes into motion. Actually, they will be lying like that only. And now, because of this applied electric field, the electrons will move and they will come into the motion. That's why thereby mobility will take place. Mobility comes from this motion. Actually, electrons will comes under motion, and with certain motion is nothing but velocity. With certain velocity, the electrons will move from valence band to the conduction band. That velocity, whatever the velocity electrons will acquire, that is called as drift velocity. What is that velocity? Drift velocity, and it is denoted by small v suffix d. That is the velocity of electron. It is meters per second. Velocity, it is meters per second, or sometimes centimeters per second. Units are very, very important. Remember, in GATE examinations, the SI units will also be expected. I think I remember that in the year in 2003, right? So they have asked that the SI units of the mobility. What is the SI unit of mobility? They have asked for 1 mark. Very, very important. That's why never neglect. Okay, you must be thoroughly prepared and thoroughly know about the each and every minute concept. Then only you can have the confidence, and you can get the full confidence in the subject, right? Therefore, this is the velocity of electron, that is called a drift velocity. Now, there is a direct relation between applied electric field and your drift velocity. Right? So your applied electric field is directly proportional to drift velocity. There is a relation between these two. What do you know? Electric field, applied electric field is directly proportional to the drift velocity. What does it mean actually? What does it mean? What does it mean? This is very important formula. Tell me, what is the importance of this formula? E proportional to Vd. What is E? E is nothing but applied electric field. This is the applied electric field. Clear? Applied electric field. What is Vd? Vd is the drift velocity. So it is directly proportional. Means that as your applied electric field will increases, as you increase the applied electric field more and more, the velocity becomes very more. Means that the electron acquires more speed actually. With greater speed, with greater velocity, I mean they jumps from here to here very fastly, very quickly, rather than if you apply very low value of a very small value of electric field, the motion is very slow. If you apply little bit larger value of applied electric field, the motion of electron is very fast. That is what directly proportional means. If a field is more, then they will move very fastly. If the field is less, they will move very slowly. That is the directly proportional. Clear? That is what the thing. Very important formula. Applied electric field is equal to Vd, small v suffix d. Now, if you remove this proportionality, then we will insert some proportionality constant. Just I want to give you some important points here. That's why I am explaining these. So, what we know that the applied electric field is directly proportional to the drift velocity. This you can write in either way. Vd proportional to your drift velocity, proportional to E, right? And drift velocity is equal to mu into E actually. Drift velocity is equal to mu into E actually. Drift velocity is equal to mu into U. Therefore, what is your mu? Mu is equal to drift velocity by electric field and is equal to, it is meters per second. This is volts per meter. Okay, volts per meter. Clear? Meters per second and it is volts per meter. And from here you can write this meter by second. Then if you reverse this, meters per volt, no? Then what you will get? Meter square volt second. This is the mobility. Meter square per volt second, or otherwise sometimes also called as meter square, or I can write here mobility is equal to meters or centimeter square. Also you can write either meter square per volt second, or otherwise also called as centimeter square per volt second. These are the SI units for mobility. Very important one. Very important one. Right? This is what about the mobility. Okay. So in this today's presentation, just we have seen the classification based on the energy band diagram of insulator we have seen, whereas next is the conductor we have seen, and third category we are going to see in the next subsequent presentation, the semiconductor. Basically, I think we will finish off this presentation here, and with some more points, okay, we will see in the next presentation. I hope you understood this, and okay, we'll meet in the next presentation. Right? Have a beautiful day.